Hello everyone. I have some great news for you today. We are entering a new unit, the unit of analytic geometry. In this unit, we are going to take the line on the Cartesian plane and we'll try to discover the formula for the length of a line segment. And along with the other formulas that we've learned in grade 9, such as midpoint of a line segment or parallel and perpendicular lines, we're going to discover some very cool features and properties of geometric shapes such as triangles and quadrilaterals, and maybe some very interesting geometry theorems as well. So let's start with the length of a line segment. So to discover the formula for the length of a line segment, I would like us to start with this very simple example where we're given a line segment on the Cartesian plane. The coordinates of the endpoints are A, 1, 1 and B, 3, 6. I'm going to follow these very short and simple steps to find the length of AB. So first we have to locate a point C below the point B, so that triangle ABC is a right angle triangle with AB as a hypotenuse. Too many words probably. In other words, what we're trying to do is locate a point somewhere on the Cartesian plane to create a right angle triangle with AB as a hypotenuse. And if you are quicker than I am here right now, you've probably figured out already that the point must be right here. And I'm going to plot this point. I'll call it the point C. And since we're here, we're going to draw the triangle as well. So from B, I'm going to draw a perpendicular towards C. And from C again, I'm going to draw the horizontal line towards A. And here I got my right angle triangle. The next step, we're asked to find the length of AC. So the length of AC is this. And if you are as practical as I am, then you probably count the squares and you say that it's 2 units, nothing wrong with that. And for BC, we go squares again, 1, 2, 3, 4, 5, 5 squares, 5 units. Okay? And now we have to find the length of AB. If I asked you to do this on your own, you could definitely do this because you know how to use the good old Pythagorean theorem in a right angle triangle. Remember that we know that this side here is 5 units and this side here is 2 units, and we're missing the hypotenuse. In here, I'm going to show you my favorite way of writing the Pythagorean theorem. I always write it in this form: hypotenuse squared equals a squared plus b squared. The reason why I do that is because very often people use the formula c squared equals a squared plus b squared incorrectly by substituting the side in here and hypotenuse in here, and that defeats the whole meaning of and purpose of using the Pythagorean theorem there. So I'm going to erase this and pretend this never happened to any of you, and we're going to substitute the a and b to find hypotenuse, or AB. So we're going to write AB squared equals 2 squared plus 5 squared, and that's 4 plus 25. I did that in my head. That's impressive. And AB squared equals 29. So that makes AB equal to square root of 29. And we're going to write units here because we are not given any specific unit measurement. And we're going to say that this is the exact answer, no rounding. And I'm going to box this up. And I'm going to say I'm done with this question. Okay? Now, I want to show you something not that important actually, but I don't know if you've ever seen people using this bar on top of the letters. It indicates that when a line segment actually is used in the formula to find the length of it, then to indicate that we draw this little bar. It's mostly the older textbooks that use it. It seems that people don't find the need to do that anymore. Okay, so now Yes, we found the length of AB, but here we were lucky we had the grid and we could count the squares. But what if we had to find the length of a line segment and we don't have a grid, or it's too big for us to measure, right? So in this case, we need a formula. So we need a more general formula that can help us find the length of a line segment. And that's why, and I brought this example here, example 2, where we can discover the formula together. Now, before we move on to the formula, I want us to talk a little bit more about the first example because numbers are easier to see and understand and make connections with. So, if I asked you what would the coordinates of the point C be in here, then you would say, well, the point C will have the same x coordinate as the point B because it's right below it, so the x coordinate will be the same. So I would write in here 3. And for the y coordinate, I would say it has to be the same as the y coordinate of the point A. So I would write in here the coordinate y equals 1. So C must have the coordinates 3 and 1. Now let's think, what is the length of AC? So the length of AC we said was equal to 2 in here. Now, do you see a connection between number 2 and the x coordinates of A and C? So 3 minus 1 equals 2, right? So it's the difference in the x coordinates that measures the length of a horizontal line. Okay? Now, for the length of 5 units that we had the other side in here, then we're going to say that, okay, so that's a vertical line, so the length of it must be the change in the y coordinates. And you can probably see the connection here. So 6 minus 1 equals 5. So that's like 6 minus 1. Okay? And we are going to say that the one of the sides of this triangle is nothing but the change in the y coordinates, and the other one is a change in the x coordinates. And in the next example, when we don't have the actual coordinates, and we're going to say that if we want to find the length of AB, where A has coordinates x1, y1, and B x2, y2, we locate a point C to make the right angle triangle. I'm going to do that right away. Here goes C. I have practice. I can do that faster now. And I will draw the right angle triangle. One here and this side in here. And we're going to say, here goes our right angle triangle, everybody. Almost perfect. And here is the right angle. What are the coordinates of C? Now we're going to say that C will have the same coordinate as the point B because it's right below it, right? So see, the x coordinate here is x2. And the y coordinate of point C will be the same as the y coordinate of the point A. So y1. And we're going to say that point C has coordinates x2, y1. Now, if we want to find the length of AC, that would be the change in the horizontal coordinate. So we're going to say that's x2 minus x1 or x1 minus x2. It doesn't really matter. We usually try to subtract the smaller number from the bigger number. So we're going to say that the length of AC is x2 minus x1. And similarly, we're going to say for the length of BC, that is y2 minus y1. Okay, it's a change in the y coordinates. So I'm going to do it this way. Okay, and this one here will be, let's go orange. So this would be, oopsie, x2 minus x1. All right, awesome. So we're going to say that the length CB is, I'm going to go back to my purple pink kind of color. So y2 minus y1. So if we want to find the hypotenuse, which is the length of AB, so we're going to say this one squared must be one side squared, so x2 minus x1 squared, plus y2 minus y1 squared. And this is a change in the x coordinates, and this is a change in the y coordinates. And we're going to say that the length of AB, which you can indicate it, and we normally do so by lowercase l, is equal to delta x, this one here would be delta x, delta, I'll show you here, x is indicated by this symbol, delta. Now, this is actually letter D in Greek, and because it's the difference, then you, instead of using the letter dx, then we use delta in here, okay? And squared plus delta y squared. And because the length in here is squared, if I want to get just the formula for the length, then I would say I need to square root the right side. And ladies and gentlemen, this is the formula for the length of a line segment. Okay? So it's a square root of delta x squared plus delta y squared. And we're going to practice this formula right away. So we are given 2 points, C and D, and we need to find the length of it. So this is how I like to do this. I list the points first. And I write C is -1, 4. And D is 3, 8. And then I call them x1, y1, x2, y2. It doesn't matter which one you call what. It's important that when they belong to the same point, they're subscripted by the same number. Now, I'm going to say that the length of CD, sorry, I'm going to use blue. Length of CD is equal to the square root of the change in the x variables plus the change in the y variables, each of them squared, and then square rooted, the whole thing. So from here, it becomes a matter of simply substituting, and I'm going to draw the perfect square root here. And we are going to write here 3 minus -1. That would be the delta x. Because I have a set of brackets, I'll use round brackets squared, plus y2 minus y1, so that makes it 8 minus 4 squared. So that would equal the square root again. Okay, 3 minus -1 is 4. That's 3 plus 1. And 8 minus 4 is 4. Oh, another 4 squared in there. Okay, too ambitious with my square root, too big. So that would be the root of 32. And the root of 32 is the same as the root of 16 times the root of 2, in case you remember from grade 9. That's 4 root 2. That's a more simplified form. Now we're going to say that the length of CD equals 4 root 2 units. Now you're probably wondering, okay, so I don't really remember how to go from here to here. It's okay, you can leave your answer as square root of 32 if you wish. Okay, it will still be marked correct. Okay. All right, so now that we know how to find the length of a line segment when we're given 2 points, we are going to practice it. Now we have to find the length of a line segment. 3, 1 and 6, 9 are the coordinates. We have to find the exact and the approximate solution. Now this is something you have to do on your own. That's your independent practice. And I think this is straightforward. It's just like the example we just did together. And the second question that you are assigned as independent practice is you're given a triangle and you know the vertices of it, and you need to classify the triangle by side length. If I were you, or I would start this way actually, I would simply draw the triangle. I'm not going to fill the color here. And you don't really need a Cartesian plane to draw the triangle precisely. Just draw any triangle. Here goes mine in here. And name the angles by letters D, E, and F. And then write the coordinates. So D is 1 and 3, E is -3 and 2, and F is -2 and 2, -2. And you have to classify the triangle by its length. Now remember that the classification we are talking about here is triangles can have all 3 sides equal. They can have 2 sides equal, or none of the sides equal. All right. Now, when all 3 sides are equal, remember that this is called an equilateral. Equal sides, right? Lateral means sides. Isosceles, very fancy term. I've never learned how and why we call it isosceles, what the roots of or the meaning of it is, and scalene. But they're all pretty names, right? So you have to check and see if you find all 3 sides equal, it's a equilateral. If you find 2 sides equals, isosceles. If none of the sides are equal, scalene. And once you know all the 3 lengths, so you have to find the lengths L1, say for example L2 and L3. So you're basically practicing the same formula that we just learned, but in 3 different examples, right? And then you classify the triangle from there. So that's your independent practice. I will post the solutions probably later, but I would really appreciate it if you try this on your own first. So I hope all this made sense, and I will see you again